Question number 4 of exercise 8.2. Given the series is n is equals to 1 to infinity 1 over 2 raised to power n minus 1 over 2 raised to power n plus 1. If we put n is equals to 1 to infinity in the given series, we will get the sum of the series. That is, we can write it like the sum of this series is, put n is equals to 1 here, we will get 1 over 2 minus 1 over 2 square plus, now put n is equals to 2 here. If we put n is equals to 2 here, we will get 2 square minus 1 over 2 cube plus up to so on up till 1 over 2 raised to power n minus 1 over 2 raised to power n plus 1. If you observe that in the first bracket, the last term can be cancelled out with this first term. And obviously this last term can be cancelled out with the next sum of the term. So it means this is telescoping sum. This is telescoping sum. Telescoping sum is the sum of the terms in which every second term is cancelled out with the third term. Or if you talk about these brackets, every second term of this bracket can be cancelled out with the every first term of the next bracket. So it means every terms will be cancelled out. Only the first and the last term will retain. So the Sn will be equals to, the sum of this series will be equals to 1 over 2 minus 1 over 2 raised to power n plus 1. Now apply the limit on this series, that is limit n approaches to infinity, Sn is equals to 1 over 2 minus 1 over 2 raised to power n plus 1, and apply limit here as well. You will get here, this term will goes to 0, so we will get here 1 over 2. So the series converges, the given series converges to 1 over 2. Now question number 5, that is sum of series from 1 to infinity 1 over 9n square plus 3n minus 2. Consider this term. Let's suppose name it as an. An is equals to 1 over 9n square plus 3n minus 2. Find out the factorization of this term and split it into two parts, like 1 over 3n plus 2 into 3n minus 1. I just made it into the 4 terms, split it into the 4 terms, and then take out the common terms and convert it into the factors like this. So we'll get 1 over 3n plus 2, 1 over into 3n minus 1. This is simple factorization. Now we can just break our this one fraction into more than one fractions by using the partial fraction method. And how we can do it? We know that this an, that is 1 over 3n plus 2 into 3n minus 1. This can be written as a over 3n plus 2 plus b over 3n minus 1. Now using the partial fraction method, find out the values of a and b. After using the partial fraction method that is already taught to you in the previous exercises, I am just applying it here, the answer. Using the partial fraction method, you will get a is equals to minus 1 over 3 and b is equals to 1 over 3. Put the values here, you will get minus 1 over 3 into 3n plus 2 plus 1 over 3 into 3n minus 1. Now you can find, now your series that was your from n is equals to 1 to infinity an, that is equals to now summation n is equals to 1 to infinity minus 1 over 3 into 3n plus 2 plus 1 over 3 into 3n minus 1, this term. Now open this series up to few terms, because you see here you have a negative and the positive sign here, and you have fractions that are somehow similar, not exactly similar, but similar in some sense, like you have the mostly the same terms here, but with opposite sign. If you put the n is equals to, from starting from n is equals to 1 to infinity, maybe you can get a telescoping sum. So let's just see that whether what you are getting here. The series will be, the sum of the series will be Sn. I am taking 1 over 3 common. You see here we have 1 over 3 common here. Now put n is equals to 1 here and there as well. You will get 1 over 2 minus 1 over 5. Now plus, put n is equals to 2 here. You will get 1 over 5 minus 1 over 8. Plus up to so on, up till 1 over 3n minus 1 minus 1 over 3n plus 2. If you observe that every second term can be cancelled out with the first term, it means again you got a telescoping sum. So in the telescoping sum, what will be the sum of the series? The sum of series will be the first and the last term. That is equals to 1 over 2 minus 1 over 3n plus 2. Now if you apply the limit here, limit n approaches to infinity, Sn, that will be equals to limit n approaches to infinity 1 over 3, 1 over 2 minus 1 over 3n plus 2. If you put infinity here, 1 over infinity will goes to 0 here. So you will be left with 1 over 3 into 1 over 2 minus 0. That will be equals to 1 over 6. So the series converges. The series converges to 1 over 6 here. Now, starting from question number 6, we must read the main question that is given on the book before the question number 6. In this question, each of the following from question number 6 till question number 10. Question number 6 to question number 10. Each of the following is the nth partial sum of an infinite series. If you observe, this is given the nth partial sum, not the series. Here you were given with the series in these questions. But now from 6 to 10 you are given with the partial sum values for the infinite series. You have to determine their series, and after finding the series you have to check whether it is convergent or not. So first of all, consider this sum of the series, that is sum of an infinite series, and find out the series. For that purpose, question number 6, that is Sn equals 3n over 4n plus 1. The sum of the series can be find out the nth term of this, basically the nth term of the series. We need to find out the nth term of the series. The nth term of the series, that is normally called as an, will be equals to your Sn minus Sn minus 1. Sn is the same term, that is 3n over 4n plus 1 minus, replace your n with n minus 1 here. You will get 3 into n minus 1 over 4 into n minus 1 plus 1. Now simplify it. You will get here 3n over 4n plus 1 minus, here you will get 3n minus 3 divided by, here you will get 4n minus 4 plus 1, that will be equals to 4n minus 3. Now simplify it, take the LCM, 4n plus 1 into 4n minus 3. You will get here 3n into 4n minus 3 minus 3n minus 3 into 4n plus 1. Now simplify it, open it, multiply the terms, and you will get here 3 over 4n minus 3 into 4n plus 1. So this is basically your nth term of this series, infinite series. Now you have to check whether it is convergent. First let it write in terms of series. Series is written in the form of the summation. So summation n is equals to 1 to infinity an, that is equals to summation n is equals to 1 to infinity, and here you will get 3 over 4n minus 3 into 4n plus 1. So this is basically your infinite series. Now we need to find out whether it is convergent or not. For that purpose, you can just find out, apply the limit on the sum of the series, that is limit n approaches to infinity Sn, that is equals to limit n approaches to infinity 3. What is your Sn? Your Sn is 3n over 4n plus 1. So this will be equals to 3n over 4n plus 1. So after applying the limit, you will get here the answer 3 over 4. How? Just take n common from the denominator. You will get 4 plus 1 over n. This n and this n can be cancelled out. Apply the limit. 1 over infinity will give you 0. So you will be left with 3 over 4 here. So the series converges and its sum is 3/4. Question number 7. Sum of the series Sn is n square over n plus 1. Now for find out the infinite geometric infinite series, that is your sum of the series from the sum of the series an will be equals to Sn minus 1. That will be equals to n square over n plus 1 minus n minus 1 whole square over n minus 1 plus 1. Just replace Sn with n minus 1 here. You will get Sn minus 1. Now simplify all the terms. You will get n square over n plus 1 minus n square minus 2n plus 1 divided by, here you will get n. After taking the LCM, this is n into n plus 1. You will get here n into n square minus n square minus 2n plus 1 into n plus 1. Open the terms. After multiplication and simplifying, you will get here n square plus n minus 1 over n into n plus 1. So your infinite series is summation n is equals to 1 to infinity an is equals to summation n is equals to 1 to infinity, and what is your an? N square plus n minus 1 over n into n plus 1. Now limit n approaches to infinity, Sn will be equals to limit n approaches to infinity. You will get here n square. What is your Sn? Sn was in your question, n square over n plus 1. N square over n plus 1 here. Now it can be written as limit n approaches to infinity, n square over, take n square common here, you will get here 1 over n plus 1 over n square here. This term and this term can be cancelled out. So you will get here limit n approaches to infinity 1 over 1 plus n plus 1 over n square. After applying the limit, you will get here 1 over infinity is 0. So whole denominator will goes to 0 here. So you will get here undefined answer. Thus the series diverges. Due to this undefined answer, your series is divergent. Question number 8. Sn is equals to 1 over 2 raised to power n. Now your an term will be equals to Sn minus Sn minus 1. That will be equals to 1 over 2 raised to power n minus 1 over 2 raised to power n minus 1 here. And here n must be greater or equals to 2. Because at the end you have to apply the limit n approaches to infinity. And for that purpose, here you must not have the negative answer. So your n must be greater or equals to 2. So you will get here, after solving, you can just solve it like, make the same thing here. You will get 2n into 2 raised to power minus 1. Now you can take easily the LCM. The two terms you can write here like this. Now this 2n and this 2n will be cancelled. You will get only 2 raised to power 1 into 2 raised to power minus 1 here. Minus, both of the terms are written here, so you will not write here anything, only here this numerator will come here. So you will get here 1 over 2 minus 1 divided by, this term can be written as 2 raised to power n minus 1. Out of this numerator, you will get minus 1 over 2, and in the denominator you will get 2 raised to power n minus 1. So from here you can write minus 1 over 2 into 2 raised to power n minus 1. And you see here this 2 has the power 1. So it will become 2 raised to power 1 plus n minus 1. You will get minus 1 over 2 raised to power n, where n is greater or equals to 2. Now your required series will be, now you need to write down your required series. Here you have written this an term for n is greater or equals to 2. If you just have n is equals to 1, if you have n is equals to 1, then your S1 will be equals to 1 over 2. So your required series is 1 over 2 minus sum of series from n is equals to 2 to infinity 1 over 2 raised to power n. This one. This sum of series that is infinite series is for n is greater or equals to 2, and before these terms you have, if you put here n is equals to 1, you will get 1 by 2. So your sum infinite series is 1 over 2 minus summation n is equals to 2 to infinity 1 over 2 raised to power n. Now apply the limit on your sum of series, that is limit n approaches to infinity Sn, that is your limit n approaches to infinity. What is your Sn in the question? That is 1 over 2 raised to power n. Out of this you will get here 0. So thus the series converges, to 1 over 2, because if you apply the limit, your this term goes to 0, so you will be left with only 1 by 2 here. So your series converges to 1 by 2. In question number 9, prove that if a positive term series an converges. Now they have given some condition. They have given us that this is convergent. They have already given us that sum of series summation 1 to infinity an is convergent. If this is convergent, then this is also convergent. So using this thing, what they have given us, we need to prove that summation 1 to infinity an into an plus 1 is also convergent. So now we have to prove summation 1 to infinity under root an plus 1 converges. Using that, summation 1 to infinity an is convergent. This is given. Using this term, we need to prove this one, that this is also convergent. For that purpose, if you observe that this thing, this is the similar as compared to the geometric mean. If you have two terms a and b, then their geometric mean will be equals to under root ab, and their arithmetic means will be equals to sum of that two terms divided by 2. We know that and an plus 1 are both positive, so their geometric mean cannot exceed the arithmetic mean. So we will write it like, since an and an plus 1 are greater or equals to 0, they are both positive, so their geometric mean will be less or equals to arithmetic mean. So geometric mean is what? Geometric mean is the multiplication of these two terms, an into an plus 1, and arithmetic mean is addition of these two terms divided by 2. So it can be written as under root an plus 1 is less or equals to 1 by 2 times an plus 1 here. What is here? We have the series. For that purpose, we need to apply here summation 1 to infinity under root an plus 1 is less or equals to 1 by 2 summation 1 to infinity an plus 1. Now we can use here this thing. Since this one is convergent, so it means our this term is convergent. If it is convergent, if you observe that if it is convergent, then by using the basic comparison test, this one is also convergent. So we can write it like, you can use here your theorem 8.16 by basic comparison test, by basic comparison test. By basic comparison test, since summation 1 to infinity an is convergent, therefore your given series, that is 1 to infinity under root an plus 1 is also convergent. So your this question number 9 is also proved here. Now come on question number 10. In question number 10, it is given. Give an example in which summation 1 to infinity an and summation 1 to infinity bn both diverges, but their sum will converge. Now we have to give here some example that will satisfy this question number 10. Let's suppose we have summation n is equals to 1 to infinity an. Now we need to select some an and some bn so that both of them are divergent but their sum is convergent. Let's suppose summation is equals to 1 to infinity is summation n is equals to 1 to infinity 1 over n square plus 1 over n. This one is your divergent. Now, let's suppose your n is equals to 1 to infinity, bn is summation n is equals to 1 to infinity 1 over 1 over n square minus 1 over n here. Or you can just take it an and take this one as bn. It's up to you. I'm just taking them just like so that this terms can be cancelled out and we will be left with this one so that it can make the p series, and you know that if p is greater than 1 then it is convergent. So now if you add up, this one is also divergent. Now summation n is equals to 1 to infinity an plus bn. This will be equals to summation n is equals to 1 to infinity 1 over n square plus 1 over n plus 1 over n square minus 1 over n. This one will be cancelled out. So you will be left with 2 into summation n is equals to 1 to infinity 1 over n square. If you observe, it is a p series. In p series, we have 1 over n raised to power p. And if p is greater than 1, then this one is your convergent series. Here p is 2. So 2 is greater than 1. So this one is your convergent series. So this one is your example for question number 10 here.